Assalamualaikum warahmatullahi wabarakatuh and good afternoon to all. I'm Dayang Norafizan binti Awangci from MTech University Technology Malaysia. Would like to present on the dual function ZIF-8 membrane for copper-2 removal. Water is a fundamental human need. Each person on Earth requires at least 20 to 50 liters of clean, safe water a day for drinking, cooking, and simply keeping themselves clean, especially during this pandemic situation. Polluted water isn't just dirty, it's deadly. During the last 100 years, industrialization has grown at a fast rate. It has thus increased the demand for exploitation of the Earth's natural resources at a careless rate, which leads to the world's problem of environmental pollution. The environment has been seriously polluted by several pollutants such as inorganic ions, organic pollutants, organometallic compounds, radioactive isotopes, gaseous pollutants, and nanoparticles. Heavy metal wastewater pollution is one of the serious issues that need to be focused nowadays. The accumulation of heavy metals from industrial activities might get into the groundwater and cause water contamination. Because of their high solubility in aquatic environments, heavy metals can be absorbed by living organisms. Once they enter the food chain, large concentration of heavy metals may accumulate in the human body. If the metals are ingested beyond the permitted concentration, they can cause serious health disorders. Copper is usually found at high concentration in wastewater because it is considered as the most valuable and commonly used metal in many industrial applications, such as metal finishing and electroplating. Moreover, copper is a very toxic metal even at low concentration, and copper-contaminated wastewater must be treated before discharging it to the environment. The permissible limit of copper ions in industrial effluents was reported by the United States Environmental Protection Agency to be 1.3 ppm, while it was stated by the World Health Organization that copper ions contained in drinking water should not exceed 2 ppm. Over the past few years, there have been numerous new methods and techniques that were developed for the removal of copper ions from industrial wastewater, such as chemical precipitation, dissolved air flotation, ion exchange, adsorption, and membrane filtration. For this study, a ZIF-8 membrane with hybrid function of both adsorption and membrane filtration was developed to synergize the performance of both the adsorption and filtration function of the membrane. In this study, the preparation of ZIF-8 membranes were done with and without the modification of alumina substrate with ABTES as linker. This is to determine the effects of ABTES on the morphology of the ZIF-8 foam. Then, the ZIF-8 membrane on modified alumina were growth using two different approaches, which are the in situ growth and layer by layer techniques. This is to determine the effects of different preparation approach on the morphology and performance of the ZIF-8 membrane. The chemical characterizations and morphology of the prepared membrane were determined using FTIR, XRD, and FISEM. For the first part, which is the effect of ABTES modification, it is obvious from the FISEM images that the membrane growth on ABTES modified alumina formed a crystallite ZIF-8 membrane with obvious hexagonal shape, the distinctive shape of ZIF-8. Whereas for ZIF-8 membrane prepared on unmodified alumina, the membrane formed a morphostate membrane with no distinct shape of ZIF-8 crystal. Therefore, it is proved that ABTES enable better growth of ZIF-8 on the surface of alumina hollow fiber membrane because ABTES can effectively enhance the heterogeneous nucleation of the ZIF-8 crystals, as mentioned by Wang et al. In 2013. The FTIR spectrum also compared the functional group existed in the ZIF-8 membrane prepared in the presence of aptase and without the presence of aptase. The intense band observed for ZIF-8 aluminum hollow fiber membrane with aptase modification revealed that the formation of ZIF-8 layer on the aluminum support. The C double bond end scratching band was identified at 1589, whereas the peak at around 1380 attributed to the entire ring scratching fingerprint. Several bands was also observed in the range of 1350 to 900, associated to the presence of in-plane bending of the ring, and the bands around 750 to 690 correlated to the existence of aromatic sp2ch bending. And the zinc end scratching band can be observed at wave number around 450. On the other hand, the ZIF-8 membrane prepared without aptase modification showed unclear ZIF-8 bands at the IR region. When we look at the XRD peaks for ZIF-8 growth on aptase-modified alumina, there are good agreement with the previous reports, thus confirming the formation of a pure crystalline ZIF-8 phase. While for the unmodified alumina surface, the growth of ZIF-8 on top of the membrane seemed to be unsuccessful, as the presence of ZIF-8 can only be detected as traces. As expected, the aptase-modified alumina membrane showed the characteristic reflection of ZIF-8 at 2 theta value of 7.3, 10.35, 12.7, 14.8, 16.4, and 18. Attribute to the 110, 200, 211, 220, 310, and 222 planes, respectively. All the membranes with aptase modification prepared at different reaction time also showed the same characteristic reflections of XRD. The ZA72, which is the ZIF prepared at the 72 hours, shows the highest intensity among all, indicated that the longer reaction time produced ZIF-8 membrane with better crystalline structure. While for membrane prepared via layer by layer, the membranes show characteristic reflection of ZIF peaks, but with rather lower intensity compared to the prior method. Whereas by comparing the intensity of one cycle membrane and 2 cycles, the 2 cycle membranes have more intense XRD peaks compared to the 1 cycle membrane. Therefore, it is noted that number of cycles affects the peak intensity. For the FTIR spectrum, the membranes have all the important peaks contributed to the existence of the ZIF-8 as mentioned earlier. It is noted that increasing the duration of reaction also contributed to the morphology of crystal form. Increasing the time has caused the increase in the membrane thickness apart from the crystal size of the ZIF-8. Whereas for membranes prepared via layer-by-layer techniques, the ZIF-8 layer form has no obvious crystallite structures, as can be seen in the FISM images of in situ solvothermal method. The layer form is also thinner as compared to the solvothermal method's membranes. Next is the results of batch adsorption study for the ZIF-8 membrane. The table shows the adsorption data analyzed via Langmuir and Friedrich isotopes. From the data obtained, the adsorption mechanism of copper-2 onto ZIF-8 membrane was best fitted with the Friedrich model, as the R2 value there is higher than the R2 value of the Langmuir model. The Friedrich model suggested that the metal ion uptake occurred on the heterogeneous surface by multi-layer adsorption. The slope, which is 1/n, implied the adsorption intensity of surface heterogeneity of the adsorbents. The surface is more heterogeneous if its value reached closer to 0. In this study, 1/n equal to 0.85, thus implies the less heterogeneity of the ZIF-8 membrane surface. On the other hand, the N describes the interaction occurred during the adsorption process. If N more than 1, it indicates the chemical interaction whereas when the N below 0 shows the physical interaction occurred. If N equal to 1, no adsorption process will occur. So in this study, the value of N is equal to 1.179. Therefore, the interaction between copper-2 and ZIF-8 membrane could be denoted as chemisorption process. The kinetic data of pseudo-first order and pseudo-second order is shown in the table. The results indicated that the adsorption kinetics of the ZIF-8 membrane is better fitted the pseudo-second order model rather than the pseudo-first order model with the correlation coefficient value of 0.9738. Hence, it can be established that the adsorption of copper-2 on ZIF-8 membrane perfectly follows the pseudo-second order kinetic model. Additionally, the value of theoretical QE from the pseudo-second order model was close to the experimental value. The filtration performance of all the prepared membranes is shown in the figure. The lowest rejection percentage is recorded by the membrane prepared via sulfur thermosynthesis at 24 hours due to the porous structure of the ZIF-8, which leads to the less rejection yet highest flux among all. The two-cycle membrane prepared via layer by layer has the highest copper-2 rejection with flux of 140. The results can be related to the compact structure of the ZIF-8 layer formed on the alumina support, which helped to reject the copper-2 ions better than the other prepared membranes. In the nutshell, Aptes modification on alumina support shows significant effect for the formation of ZIF-8 crystal structure membrane. ZIF-8 membranes prepared via in situ solver-thermal method have higher crystallinity compared to the membranes prepared via layer-by-layer method, increasing the duration of the reaction time in the in situ solver-thermal method produced more thicker ZIF-8 membrane with almost the same crystal structure in comparison with the shorter synthesis time membrane. The batch adsorption study of copper-2 on ZIF-8 membrane reveals that the adsorption mechanism is well fitted with the Friedrich and pseudo-second order model for the isotherm and kinetic study respectively. Lastly, the filtration of copper-2 ion solution can remove up to 90% of copper-2 ions with the flux of 150. Okay, that is all from me. Thank you.